So today we're going to look at 5.3, which is diagonalization, and this is going off of the last thing that we did in 5.2, where we looked at what it meant for matrices to be similar. So a matrix A, it's got to be a square matrix, so it's got to be an n by n matrix. So a square matrix A is diagonalizable if A is similar to a diagonal matrix D. So that means that we can find this invertible matrix P such that A is equal to P, D, P inverse. D is just going to be a diagonal matrix. So that means that it's got non-zero entries, or at least some non-zero entries on that diagonal D. They don't all have to be zero, don't all have to be non-zero, but you should have at least one non-zero entry in there. So you've got a diagonal matrix, and then you've got some invertible matrix P such that A is equal to P, D, P inverse. Okay. Why do we like doing this? Well, there's a couple of reasons why. The first reason that we like to write a matrix in its diagonalizable form is because it makes it really, really simple to find powers of a matrix. So if I wanted to say find A to the power K, what I could do, if I wanted to do this a really long way to start with, is to multiply A by itself K times. So I could do PD, P inverse, PD, P inverse, and multiply them all together K times. So you've done this K times. Okay. Now, this thing will actually shrink down and it will simplify a lot, because if I rearrange this slightly and change where my parentheses are, I've got P, D, and then I've got P inverse times P. Then I've got D, and then my next term would be P inverse times P. And then I'll have D, and it's going to keep going all the way down to P inverse, P, D, P inverse. Okay? All of these P inverse P's are going to cancel down to the identity. So all the way along, you're going to get D times the identity, D times the identity, D times the identity, etc. So this actually simplifies down to P. Then I'm going to have with D times the identity, that's going to happen K times. So I actually end up having D K times. And then at the end, you'll see I've got the identity times D, so that would be the last D that I would have there, multiplied by P inverse. So if I've got a diagonalizable matrix A, if I want to take a power of it, I can simply do this, which means that if I know what that matrix P is, that will make it similar to this diagonal matrix D, all I would have to do is take this diagonal matrix D and take that to the power K, and then all I have to do is do P times that matrix times P inverse. Now, taking a power of a diagonal matrix is super simple. So if I were to, let's say, this is just a small example, take this matrix cubed, all I have to do in this case, and you can do this for yourself using matrix multiplication to prove that this is actually true, all I have to do is take that power of the diagonal entries. Okay, you would have to do this by matrix multiplication by doing like row times column, etc., as we normally do, but this is what you would find. So if you ever take a power of a diagonal matrix, it's simply taking the powers of the entries on the diagonal. So it's way easier to take that exponent of the diagonal matrix than it is of the original matrix. So if I know what that matrix P is and I can find D, this is really easy, okay, to take any power of A. They do this in particular if you've got like really, really big matrices and a high power, particularly in like computer problems and stuff. Like if you're trying to code this, it's actually much quicker to do it this way than it is to constantly take those powers of the larger matrix A. Okay, where does P and D come from? Okay, that's what we want to look at now. This is called the Diagonalization Theorem. So the Diagonalization Theorem. Okay, and there's a couple of things to note in here. So, an n by n matrix A is diagonalizable if and only if A has n linearly independent and also distinct, but that kind of goes along with the linearly independent part, eigenvectors. Okay, you can find P and D for this matrix A. So A would be similar to a diagonal matrix and hence it would be diagonalizable if and only if A has n linearly independent eigenvectors. Okay, so you should be able to find n eigenvectors for a particular matrix A. Kind of coming off the back of that, if we do A is equal to PD P inverse with diagonal matrix D, so this happens if and only if the columns of P turn out to be the n linearly independent eigenvectors of A. And as you can probably guess, if the columns of P have the eigenvectors in them, the diagonal entries in the matrix D are just the associated eigenvalues for each of the eigenvectors. Okay, so we can build P and D as long as A has n eigenvalues, and they do not need to be distinct. That's totally fine. They do not need to be distinct, but you will have to put any repetitions into D as well. So the diagonal of D has the eigenvalues on that diagonal, and then P is made up of the eigenvectors that go with each of the eigenvalues. Okay. So it means that A is diagonalizable, so it can be written as PDP inverse, as long as it has n linearly independent eigenvectors. And if it has n linearly independent eigenvectors coming down from here, okay, there's n of them and they are linearly independent, going back to what we know before, okay, that must mean that they form a basis for Rn. Okay, so because you have n linearly independent eigenvectors, that means the eigenvectors of A form a basis for Rn. And we actually call that the eigenvector basis for Rn. Okay, so we've got exactly n linearly independent vectors, okay, within an n by n matrix. Therefore, that means that they must form a basis for Rn. Okay, quick proof for this. So P has n columns. We'll call them V1 through Vn, okay? And each one of those vectors has n entries in it, okay? So P is basically an n by n matrix, and D is the diagonal matrix. I'm going to call them lambda 1 up to lambda n because we know what they end up at, but we need to show that that is the case. Okay, so on my diagonal matrix, I've got these random values, lambda 1 through lambda n on the diagonal. Above the diagonal, I've got all zeros. Below the diagonal, I've got all zeros. So all I know right now is that A is diagonalizable. So I know that A is equal to P, D, P inverse. Because we know how inverse matrices work, what I can do is multiply on the right on both sides by P. If I do that, on the left I'm going to get A times P, and if I multiply this on the right by P, I'd get P inverse P at the end, which is just the identity. So that would give me AP is equal to P times D. So I'm going to write this out. If P has those n columns, V1 through Vn, I'm going to write that in terms of its columns. So A times P would be A, V1 through Vn on P. Again, P is V1 through Vn as its columns. And then D is just this matrix with zeros above and below it, not just 1 0. There's a ton of zeros up there. So we've got this set up. Now, thinking about how matrix multiplication works, okay? On the left-hand side, if I've got a matrix multiplied by another matrix where I've split it into its columns, I know that this thing here, its columns are going to be A, V1, A, V2, A, V3, etc. So each of its columns is going to be A times Vi. Okay. And on the right, what you should notice, because we've got a diagonal matrix there, just looking at V1 for now, okay, it's only ever going to be the entries in V1 that are going to multiply lambda 1, okay? Because it's in that top left-hand corner, and the only things that will ever multiply it are the entries from V1. Go down to lambda 2. The only entries in this matrix here that will ever multiply lambda 2 are the entries in V2. You can keep going with this, and you should find out that it's only the entries in Vi that will ever multiply lambda I, okay? Lambda I is just a scalar, so I can bring that out the front to give me that, okay? So this is the case for all I, so it's true for all I. So I always have AV1 is equal to lambda V1, AV2 is lambda V2, etc. Now, are these things eigenvector, eigenvalue pairs? Well, the only thing that I need to make sure of right now, number one, I want to find out if they're linearly independent because that's what the theorem says, but I need to make sure that they are actually eigenvector, eigenvalue pairs with lambda I and Vi. Quick argument for why they're linearly independent, okay? They're the columns of the matrix P. We've said up here, at this point here, that P is invertible. We know that we can find P inverse. So because P is set up to be invertible by the invertible matrix theorem, that must mean that its columns are linearly independent. So by the invertible matrix theorem, because P is invertible, the VI's are linearly independent. Okay, we know that the columns of P must therefore be linearly independent. So I know that I have n linearly independent vectors. The question is, why are they eigenvectors? Well, The only thing that we need to make sure of is that they are non-zero. Okay, as long as we have a non-zero x here, such that a times x is equal to lambda x, then that must mean that x is the eigenvector, lambda is the eigenvalue, okay, by definition. So I just need to make sure that this thing is non-zero. Well, that comes off the back of this linear independence, okay? If any one of those columns vi was 0, we would have a linearly dependent set, okay? So we know any set of vectors that contains the 0 vector is linearly dependent. Well, here we know that they're linearly independent. That means that it cannot contain the 0 vector. So we know that we have non-zero vectors with these lambdas that go with it. So therefore we must have eigenvector eigenvalue pairs. So because, let me come over here, because the 0 vector cannot be in a linearly independent set, this implies lambda I, vi are eigenvalue eigenvector pairs. Okay, so for each lambda I, you've got a vi such that they give you an eigenvalue and an eigenvector for the matrix A. Okay, if you wanted to go the other way around, to show that you know that they're linearly independent, etc., and you want to go backwards to show that it's diagonalizable, all you would have to do is to make a matrix D out of the eigenvalues. So if I just, to go the other way, so what we've done up here goes this way, showing that if it's diagonalizable, therefore they're eigenvectors and eigenvalues, and the eigenvectors are linearly independent. We now want to go the other way, okay? So we want to show that given these linearly independent eigenvectors with these eigenvalues associated with them, does that mean that this matrix is diagonalizable? Well, all we have to do to go this way is to say, okay, we'll make that matrix D out of the eigenvalues, and then make this matrix P out of the eigenvectors. Okay, so we know that they're eigenvalues and we know that they're eigenvectors, okay? And we know that they are linearly independent. So all you have to do now, because you know that AVI is equal to lambda VI, kind of going backwards on what we did here, okay? You could do this calculation backwards. So what you can do here is just say, okay, because I know that this is the case, I can write it as this, which therefore gives me this. So all you're doing is that calculation, but backwards. So you know that AP is equal to PD. Now at this point, you need to implement the fact that the columns of P are linearly independent. Because they are linearly independent, we can invert P. So we can say that A is equal to PD, P inverse, okay? So you can go both ways on this. If you know it's diagonalizable, you now know that you can write them as eigenvectors and eigenvalues where the eigenvectors are linearly independent. Going the other way, if you know that this thing has eigenvectors and eigenvalues and that the eigenvectors are linearly independent, you know that the matrix A is diagonalizable. So we can go both ways on this. Okay, let's do this example. So diagonalize the matrix. This is something that you would get in like a test or something because it's like a small example. I don't want to give you massive examples that are going to take you forever to do. I will show you one that takes a while to do at the end, but I will do some shortcuts because you would never have to do anything that large. You may have to do something like this in the homework, but I would never give it to you in a test because, as I said before, trying to solve like cubics and stuff like we were doing in the 5.2 video where I said solving cubics is a nightmare. Don't worry about it because I may give you something on the homework where you may have to do some working out for it. But I mean, for most of the time, I will give you something like this where it's a 2 by 2 and it will be easy to find the eigenvectors and eigenvalues. So if I want to diagonalize the matrix, we know that you have to find your eigenvalues first, and then for each eigenvalue you find its eigenvectors. So first of all, let's find the eigenvalues. So the determinant of a minus lambda I is equal to 0. So that means if I find the determinant of a minus lambda I, well, a minus lambda I, as I said before, all you end up doing is actually subtracting lambda off of the diagonal elements. So you would get 6 minus lambda and 3 minus lambda. So if I take the determinant of this and then I want to set it equal to 0, the determinant of that is equal to, it's AD minus BC. So that's going to be 6 minus lambda, 3 minus lambda, and then plus 2 will equal 0. If you multiply that out, what you should get, I will tell you what you get in the end. If you multiply this thing all out, you should get lambda squared minus 9 lambda plus 20 is equal to 0. We want two numbers that add to -9 and multiply to 20. So it's going to be -4 and -5. So you're going to get lambda minus 4, lambda minus 5 is equal to 0. Therefore, lambda is equal to 4, lambda is equal to 5. So we have our two eigenvalues. Now we need to find the eigenvectors associated with those eigenvalues. So for lambda is equal to 4. To find eigenvectors, you have to go back to this form of the equation. And you need to solve for x. Okay, so we're going to have a minus 4i, because lambda is equal to 4 here, is equal to 0. So let's go back and see what that would be. So I'm going to be looking at this matrix here. Wherever I've got a lambda, I need to put 4. So that's going to give me 2, -1, 2, -1. So I'm going to get 2, -1, 2, -1 times x1, x2 is 0, 0. Okay, so to solve this system, you make an augmented matrix. And then you're going to reduce row echelon form it. And if you do that, I won't go, well, I could go all the way down, I guess. You should get this as the reduced row echelon form. So we know that x1 minus 1/2 x2 is equal to 0 and x2 is free. Okay. So many ways that you could solve this thing here. What I'm going to do is I'm actually going to rewrite that as x2 is equal to 2x1 just to make it easy. Or you could write x1 is equal to 1/2 x2. Whichever way you want to write it, it's up to you. Okay, so if you do this, you've got a free variable. Okay, I always set that free variable equal to 1 to find the simplest possible way that you could do this. But in this case, I'm going to set it to something slightly different because we've got a fraction here, okay? You could set your free variable to be whatever you like, okay? Either way, it's going to give you a basis, okay? It will give you a basis vector for the eigenspace that's associated with that eigenvalue. So in this case, if I had set my free variable equal to 1, I'd get 1/2 1 as an eigenvector. Now that is true, that is an eigenvector. But I don't like the fraction in there. You can by all means leave it in there. It does not matter, okay? You can leave it in there. But what I'm actually going to do here is that I'm going to multiply this thing through by 2 to give me 1, 2. Because any multiple of this thing is also an eigenvector for A, okay? Because I can set x2 equal to anything that I like, and that thing would still be an eigenvector. So x2 can be equal to anything. x1 then depends on x2. But whatever value I set x2 to be, I'm still going to get an eigenvector out, okay? So we can write this the long way. So I know that my solution to this system is this, okay? So I could set x2 to be whatever I like. To get rid of that fraction, I'm going to set x2 equal to 2. So the eigenspace, that will give me my basis vector, and then I can take any multiple of that, will also be an eigenvector for A. So the eigenspace of A associated with eigenvalue lambda is equal to 4 has a basis. Okay, just to make sure that I've got whole numbers, I'm going to set that as my basis. Okay, now we've got to do the other eigenvalue. So find the eigenvectors for lambda is equal to 5. So this time I need to go back and I need to solve this. So a minus 5i, let's go back to here. A minus 5i, so I'm going to be setting lambda is equal to 5 here. So that's going to give me 1, negative 1, 2, negative 2. So I'm going to get 1, negative 1, 2, negative 2. X1, x2 is equal to 0, 0. Okay. Set that up as an augmented matrix. And then you're going to take the reduced row echelon form of that augmented matrix to give you this. Okay. Again, x2 is free and x1 minus x2 is 0. So x1 minus x2 is equal to 0. x2 is free. So my solution, x, is equal to x2. Then because x1 is equal to x2, because of this, rearrange that, you get x1 is equal to x2. So your solution, x1 is equal to x2, will give you that. Okay. x2 can equal anything that you like. So therefore, this vector here forms my basis for the eigenspace associated with lambda is equal to 5. And any multiple of that vector will give me an eigenvector associated with lambda is equal to 5. Okay. Now, I have my eigenvalues and I have my eigenvectors. We now need to set up, because remember the problem was to diagonalize the matrix A. So I need to find P and D such that this is true. Okay. So A that we got was 6, negative 1, 2, 3. Then when you find P, make sure whatever order you put your eigenvectors in P, you put your eigenvalues in D in the same positions. Okay. So let's start out. The first eigenvector that I found, which was for lambda is equal to 4, was 1, 2. You could take any multiple of that, you would still get the correct answer. So 1, 2 is going to be my first one. Then I'll take the eigenvector for lambda is equal to 5, which was 1, 1. Now, the first eigenvector that I dealt with was associated with lambda is equal to 4. So I have to put 4 as my first eigenvalue in D. Then the next eigenvalue was 5, okay? So my first eigenvector here was associated with lambda is equal to 4. My second one was associated with lambda is equal to 5. So make sure you put them in the right positions. And then if you want to, you can find the inverse of this, but I tend to just write it as P inverse. But you can go ahead and find that if you want. But this would be the answer that I'm looking for to diagonalize the matrix, okay? If you want to look at a 3x3 example of this, by all means, it is there for you to look at. It's on, so a 3x3 example is on page 285 if you would like to look at it. Again, when you come back to the tricky part with a 3x3 is this part here, because solving a quadratic we know is really easy. Solving a cubic is not so easy unless there is an obvious factor there. So just be aware of that. There is that 3x3 example that you can look at, but I would, if I gave you a cubic, it would be super simple and you would be able to see the solution pretty quickly. Okay, so that's page 285. Now, everything we have looked at so far has dealt with having distinct eigenvalues. However, 9 times out of 10, you're going to end up with a repeated eigenvalue somewhere. So it's going to have a multiplicity greater than 1. So it may occur twice, 3 times, 4 times, however many times it may be. But remember, all the multiplicities must add up to n. So you can't have, let's say, an eigenvalue with multiplicity 4 for a 3 by 3 matrix. Okay, it doesn't work. All of the multiplicities added together have to equal n for an n by n matrix. So everything we've looked at so far, like let's go back to what we had here. We had our eigenvalues 4 and 5, each have multiplicity 1. 1 plus 1 is 2. We were dealing with a 2 by 2 matrix. Okay. Now we want to look at if they have a multiplicity of greater than 1. And what will this thing look like? Can we still diagonalize it? The answer is yes, but finding the eigenvectors, there's a slight catch to it, where you have to do a bit more work for it. So, sometimes all of the eigenvalues are not distinct. So some have a multiplicity greater than 1. Okay. Now, we know that the eigenvectors associated with the distinct eigenvalues are linearly independent. Okay, we saw that in the last video. So if we have, let's say, k distinct eigenvalues, their eigenvectors are linearly independent. The question is, if you don't have distinct eigenvalues, are their eigenvectors still linearly independent? The answer is yes, as long as this thing is diagonalizable. Okay? We'll do a quick example in a minute where you will see how this works. But if you come back to here, I'll give you a very quick explanation. Come back to what we did here. Okay, this was the formula that we used, okay, whatever your lambda is here it was 5. We used this formula to find the eigenvectors x that were associated with that particular lambda. What we are doing here, if you look at it, is we are solving for the null space of A minus lambda I. Okay, so we're solving for the null space of a matrix. And we get those solutions x for the null space of the matrix. If you remember back to when we looked at null space, okay, the way that we found the basis for a null space, so the linearly independent vectors that span that null space, was we just solved it. So we went ahead and solved it. And whatever vectors we got out here, so you had a free variable times a vector plus a free variable times a vector, etc. Those vectors form the basis for the null space because they were linearly independent. Okay, so it's the same deal here. Even if your eigenvalues are not distinct, as long as your eigenspace has a basis that has dimension equal to its multiplicity. So here we had one eigenvector associated with an eigenvalue that had multiplicity 1. If I had a multiplicity of an eigenvalue that was, let's say, 2, I would need 2 vectors in my eigenspace for that basis. Okay, so the number of vectors that I have in the basis for the eigenspace, the number of things that I can find when I try to find the eigenvectors here for that particular lambda, okay, the number of vectors that I get should equal the multiplicity of that eigenvalue. If that is true, then this thing is diagonalizable, okay? So we know that sometimes they're not distinct. Then, if a matrix, or an n by n matrix, has n distinct eigenvalues, we know that its eigenvectors are linearly independent. Okay, we found that last time. Okay. Question is, when you don't have these distinct eigenvalues, what happens? Well, we know already the eigenspace, so the basis vectors for the eigenvalues of A, so we could take any linear combination of the vectors in the eigenspace, and that will give us an eigenvector associated with eigenvalue lambda. So the eigenspace of each distinct eigenvalue has dimension that is less than or equal to the multiplicity of lambda k. So for each eigenvalue, okay, the eigenspace, so the basis that you get here, okay, the number of vectors in that is always less than or equal to the multiplicity of that particular eigenvalue. So if you have an eigenvalue with multiplicity 3, the eigenspace should have a basis that has dimension no more than 3. Okay, it can have at most 3 vectors in that basis. Okay, so whatever the multiplicity of that eigenvalue is, that is the maximum dimension of that eigenspace. Okay, that's always the case regardless. So you could have an eigenvalue with multiplicity 2, but its eigenspace only has 1 vector in it. In that case, it is not diagonalizable. Okay, in order for this thing to be diagonalizable, so A is diagonalizable and can be written as A is equal to PDP inverse, if and only if the characteristic polynomial or the characteristic equation, number 1 goes into all linear factors. Okay, so I should be able to, let's come back to here. Okay, whatever I get for my characteristic equation, whatever I get for that polynomial, I should be able to factor it into all linear factors. If you ever end up with a factor that's like a quadratic that can't be factored out into linear factors, then you know that this thing is not diagonalizable. You have to be able to get this thing completely factored into all linear factors. Otherwise, you're going to end up with a case, well, probably where you've got complex eigenvalues that we'll look at later. But you should be able to get this thing into all linear factors. So the characteristic polynomial factors into all linear factors. Okay, you can have some of those linear factors be repeated, that's fine, but just make sure that it can be completely broken up into linear factors, because then that means it will have n roots. Okay, that's what we're really looking for here. So it means that it's got n eigenvalues. So you know that it needs to have all linear factors. And this is what I was saying before, the dimension of the eigenspace of each lambda k is equal to the multiplicity of lambda k. So in order for this thing to be diagonalizable, we already know that the dimension of the eigenspace is going to be less than or equal to the multiplicity, but for it to be diagonalizable, it has to equal the multiplicity of lambda. Otherwise, this thing cannot be written in terms of the eigenvectors and eigenvalues. Okay, you have to have the same number of eigenvectors as you do eigenvalues. So if an eigenvalue has multiplicity 2, it's got to have 2 vectors in the basis for the eigenspace in order to write it as PDP inverse. Okay. Just as another side note, if A is diagonalizable, and take BK to be the basis of the eigenspace of A associated with lambda K. So where lambda K are each of your distinct eigenvalues. So if you've got any repeated ones, they should all be within one here. So if you've got, let's say, an eigenvalue with multiplicity 3, you're going to have 3 vectors in the basis for that distinct eigenvalue. Okay. So if each one of those is a basis for the associated lambda K, then if I put all of those bases together, so I'm going to end up with n vectors in total. Okay, that will give you the eigenvector basis for Rn. I'll call it B1 through BP. Okay, so I've got a diagonalizable matrix A. Okay, because of that, I know that because it's diagonalizable, that there are going to be n eigenvectors in total. Okay, because each lambda K, which has multiplicity, whatever it may be, the eigenspace associated with that lambda K is going to have the same number of vectors in it as the multiplicity of lambda K. So I know that in total I have n eigenvalues, even though some of those may be repeated, but the sum of the multiplicities is n. Therefore, the number of eigenvectors that I have in total is n. They must be linearly independent because I already know for the distinct eigenvalues, the eigenvectors are linearly independent. If I have any repeated eigenvalues, I know because I am solving a null space of a matrix that they are automatically going to give me linearly independent vectors back as a solution. So I know that for my eigenvalues, as long as I have the multiplicities equal to the dimension of the eigenspace, I know that I'm going to have n eigenvalues and n eigenvectors that are linearly independent. Therefore, those eigenvectors form a basis for Rn. Okay. Now, let's do an example. I'm not going to go through all of this. In the notes, what page am I on here? Page 5 of the notes. Because this is going to give me a cubic, because I'm looking at a 3 by 3 matrix, I have written out how I solved this as a cubic. But it's a page-long calculation, so I'm not going to go through that here. But I will tell you what it factors out to, and if you want to see how I did it, it is on the notes for this chapter on page 5. So I'm going to diagonalize the matrix A is equal to 2, 2, negative 1, 1, 3, negative 1, negative 1, negative 2, and 2. So I'm going to diagonalize this matrix. So I need to find its eigenvalues and eigenvectors. You're going to, I'll tell you how I did this, but I'm not going to go through all of it. You need the determinant of A minus lambda I is equal to 0, and you solve that for lambda. So when you do this, you are finding the determinant A minus lambda I just takes lambda off of the diagonal entries. So that'll give me 3 minus lambda, negative 2, negative 1, negative 1, 2 minus lambda is equal to 0. Okay. There's no obvious row or column that contains a lot of zeros. So using the cofactor method here is a nightmare. Okay, just as a heads up. If I ever gave you one of these in an exam, I would give you a matrix that, let's say, had like a 0 here and a 0 here, just to make it easier, because then you could expand around like this entry. And it makes it so much easier to find the determinant of a 3 by 3 when you have the majority of entries in a particular row or column equal to 0, because then you can just use the cofactor method and expand around that row or column. Is way easier. So yeah, I went ahead and found the determinant of this 3 by 3 as we normally do. I'll tell you what it comes out to. You should get, once it's factored, because it's the factored part that is annoying here. That's what I end up with. So I know I've got a lambda minus 1 squared here. So I know that lambda is equal to 1 and lambda is equal to 5. But lambda equals 1 because this thing is lambda minus 1 squared times 5 minus lambda equal to 0. Okay. Lambda equals 1 has a multiplicity of 2. Okay. It occurs twice, 5 occurs once. So as I said, if you want to see how I got down to that, just look at page 5 on the notes. Then what I did was I had to find the eigenspace associated with lambda is equal to 1 and lambda is equal to 5. Okay. So eigenvectors or eigenspace for lambda is equal to 1. Okay. What you're going to be solving here is a minus 1 times I times x is equal to 0. If you do that, what you should get is 1, 2, negative 1, 1, 2, negative 1, negative 1, negative 2, 1, x1, x2, x3 is 0, 0, 0. Okay, so all I did was I came back to a minus lambda I, which is this matrix here, and I took a minus 1i. So all I did was plug in lambda is equal to 1. And that is the matrix that I got here. Then you can form an augmented matrix and you can use Gauss-Jordan to get it into reduced row echelon form in order to solve this system. So if you do that to find the reduced row echelon form, you should get, you can probably see it from this matrix here, that is what you get. I have 2 free variables, okay? So what I actually get is x1 plus 2x2 minus x3 is equal to 0. x2 and x3 are free variables. Okay. So because I've got 2 free variables here, I already know I'm going to get 2 vectors within the basis of my eigenspace, which is what I want because this thing has multiplicity 2. Okay, so I know I'm in the right direction here. So the number of free variables that you get here should equal the multiplicity of the eigenvalue, because that means that you're going to get that number of vectors in the eigenspace. If you don't do that, if you don't get that when you try and solve this, then you know that this thing is not diagonalizable. So if I went ahead and did this and only got 1 free variable, that would mean I would only have 1 vector in the basis of my eigenspace. Okay? So that would mean that the basis of my eigenspace had a different dimension than the multiplicity of the eigenvalue, and therefore it's not diagonalizable. Okay. But here what I would get is x is equal to the solution of this. You can go ahead and write all of this out, but I'm going to skip a step. And this is the solution for that system. Okay, you just rewrite out that equation, give you x1 in terms of x2 and x3, and that is the solution. Okay, so my eigenspace of A associated with lambda is equal to 1 has basis of the 2 eigenvectors that I got down here, because if I take any linear combination of those 2 vectors, so I let x2 and x3 equal to anything that I like, I'm still going to get an eigenvector x that satisfies this equation. Okay, that's just the eigenvector eigenvalue equation rearranged. So any x that is a linear combination of these 2 vectors satisfies ax is equal to lambda x. So I know that this is the basis for my eigenspace. Any linear combination of these two vectors is an eigenvector of A associated with lambda is equal to 1. Okay. Now, the next thing that I want to do is find the eigenvectors for lambda is equal to 5. So I'm going to be solving a minus 5i times x is equal to 0. Again, you can go ahead and do this. If you come back to here, all you're going to be doing is plugging lambda is equal to 5 into this matrix here. Okay, plugging lambda is equal to 5 into that, and then doing that times x is equal to 0. So if you do that, you're going to get negative 3, 2, negative 1, 1, negative 2, negative 1, negative 1, negative 2, negative 3 is what you should get when you do that. You can try it yourself. Should equal the 0 vector. Okay, so again, you want to solve this system. So I'll find an augmented matrix with the 0 vector, and reduced row echelon form of this should give you this matrix. Okay, so this time we only have one free variable. x3 is the only free variable that I get, and x1 and x2 will depend on it. So what this gives me here is x1 plus x3 is equal to 0, x2 plus x3 is equal to 0, x3 is free. Okay, so that means x1 is negative x3, x2 is also negative x3, x3 is free. So that means that my solution x is just going to depend on x3. It's going to look like that. So the eigenspace of A associated with lambda is equal to 5 has a basis of just that one vector. It's any multiple of this one vector. Okay, so I have all my eigenvalues and all of my eigenvectors. Okay, and I know that I have the correct number of eigenvectors because the eigenspace that is related to each one has the same dimension as the multiplicity of that particular eigenvalue. Okay, so that tells me I'm going to put P into as a matrix. So first two columns of P I'm going to put as these two. You can put it as the other vector if you particularly want to, just then make sure you put your eigenvalues the right way around in D. So I'm going to put P as negative 2, 1, 0, 1, 0, 1. And then I'm going to do the eigenvector for 5. So the basis vector there is that. And D, okay. Now, I put in my eigenspace vectors first that were associated with lambda is equal to 1. So they are going to be my first two diagonal entries in D. Okay, remember to put it twice, it's got multiplicity 2, it's repeated. And then the last eigenvalue was 5. Okay, so we have completely diagonalized A as PD, P inverse for a particular A, and P was this and D was this. Okay, if you have any questions on this, please feel free to ask me and I will be more than happy to help, and I will see you in the next video.